The detection of planets around other stars is one of the most exciting discoveries in all of science in the last few decades. Starting in 1995, a new field has opened up as we found planets around other stars, starting with Jupiter and super-Jupiter mass, moving towards Earth mass planets and terrestrial planets. Who could have imagined 20 years ago that around a system in the constellation Cancer, we might visualize and eventually detect multiple planets, gas giants, in solar system type orbits around a nearby star. A plot of the discovery of planets in these last 20 years around other stars gives a sense of the dramatic progress. This is a logarithmic scale of mass, and the limit on mass detection for planets has marched steadily downward from the initial discoveries, which were Jupiter mass or larger, to reach Earth mass just in the last few years. The last couple of years has been overwhelmed by the discoveries from the Kepler telescope in space, launched by NASA. In addition to the steady march of a downward mass limit on the lowest mass planet detected, the numbers have continued to accumulate, with a doubling time in the number of exoplanets of between 18 and 24 months. Extrasolar planets, or exoplanets, are one of the most hot topics in astronomy at the moment. The first discoveries puzzled astronomers enormously, because rather than finding giant planets in typical giant planet orbits, they found hot Jupiters on incredibly tight, hot orbits of their parent Sun-like stars. Their very first exoplanet discovered, 51 Peg, is in a 4.4-day orbit around its Sun-like star. Think, Mercury takes 88 days to orbit the Sun, so this is a Jupiter-mass planet far closer to its star than Mercury is to the Sun. Many of the early discoveries were like this, so-called hot Jupiters, and astrophysicists were confused because they had no way of explaining how giant planets could possibly form so close to their parent stars. Even with 100 or so detections coming in the late 1990s, it was clear that there were lower mass planets ready to be found. The distribution of masses of the planets found at any point in the last few decades rises rapidly towards the detection limit. That's always a sign that there are low mass planets lurking just below the detection limit. Imagine you were a fisherman and had a net with 1-inch holes, and your net was filled with fish, maybe a few that were a few feet long, many that were a foot long, and a large number 3 or 4 inches, bigger than the whole size of your net. The rising number of fish towards the size of holes in your net is an indication that there are indeed many fish to be found that are just too small for your net to catch. Astronomers also have needed better nets to net the small planets that are out there. As of early 2013, there are over 3,000 exoplanets known. Many of these remain to be confirmed, but in all likelihood they will be, because Kepler detections have a 90% probability of being confirmed once they have sufficient data. Many of these are Jupiter mass, and most are more massive than Uranus and Neptune, but gradually the detection limit has reached towards super-Earths and Earths, and there's every expectation that a very large number, perhaps the majority of exoplanets, are small, rocky, terrestrial planets. The presence of so many giant planets so close to their stars forces a revision of our idea of how the solar system formed, and other solar systems, because there's no way for planets to form that large, that close. There's not enough material, and there's no way for that material to condense and go into an object in a stable orbit. The early exoplanet discoveries had other puzzles too. When people plotted out the eccentricity of the orbits, or the degree with which they deviate from circularity, these planets were in much more elliptical or eccentric orbits than the planets in the solar system. In fact, most of the first few hundred exoplanets had eccentricities of 10 or 20%, which is rare in the solar system. Nobody could explain why the orbits were so eccentric. The excitement of discovering exoplanets was tinged with frustration because people could not explain how these planets formed. It seems now that planets can migrate, and that planetary migration has to be a standard part of the way solar systems work. Not only that, but planets go through periods in the history of a solar system where their orbits are unstable. They can change places, move inward or even outward, and occasionally get ejected from the system entirely. Computer models have been essential in helping us understand the chaotic motions and orbits of solar systems. These new models applied to our solar system suggest that the giant planets have not always been in the positions they hold now. In fact, there's indirect evidence that Uranus and Neptune swapped places early in the history of the solar system, and that this rearrangement was associated with a perturbation to the comet cloud that produced a spike in the impacts on the Earth and the terrestrial planets. If true, this solves a mystery of several decades standing, whereby there's an era of heavy bombardment about 3.8 to 3.9 billion years ago, present in the cratering record on the Moon and Mars and Mercury. There needs to be a reason to explain this heavy bombardment, because in general, after a solar system formed, the amount of heavy rocky debris objects diminishes with time as they form planets and are swept away. There should be a continuous decrease in the cratering rate. Instead, we see a spike 3.8 to 3.9 billion years ago, presumably impacting the Earth too, but the cratering record is not good on this planet because of erosion and tectonic activity. In some ways, we can think of the way planets behave as a game of cosmic billiards. A very violent history early on as the planets formed, and then occasional violence later on as the planetary systems go through instabilities. Some of these instabilities are triggered by resonances, such as when giant planets enter orbital states where the ratio of the periods is a whole number, 2 to 1 or 3 to 1 or 3 to 2. These resonances have been observed in the moons of giant planet systems, but they could apply to the giant planets themselves. Planetary migration is now a standard part of the theory of how solar systems form. Put simply, it is impossible to form a hot Jupiter in its place. It must have formed further out and migrated in. While migrating in, it might fall into the parent star or park in an orbit and form a stabilized facing position, tidally locked to the parent star. No one was present when these events happened, so it's very hard to verify these models. We have to look for subtle clues in the current placement of the planets and in the behavior of the comets, asteroids, and meteors. Another way to think of this is the fact that the solar system is essentially full in dynamical terms. We can visualize the solar system, and we know that the space between planets is vastly larger than the size of the planets themselves. The solar system indeed seems like mostly empty space. But if you play a game in a computer where you take the current arrangement of the solar system and try to drop a small terrestrial planet somewhere else, such as between the orbits of Mars and Venus, or even in the outer solar system, it causes chaos. It upsets the orbits of the giant planets and occasionally ejects one from the system. In that sense, the solar system is full. It contains about as many objects as it could and still be long-term stable. The solar system, having undergone rearrangements early in its history, does now appear to be stable. If we run these models forward for our solar system, the planets stay in their current orbits for at least 1 billion years. The models with good computers are now capable of showing how terrestrial and giant planets might have formed. We have plausible creation scenarios. For terrestrial planets, it's a situation where planetesimals, rocks of maybe 100 to 1,000 kilometers in size, about the size of the largest asteroids, maybe a few thousand are present at the beginning, and in a few tens of millions of years, they collide, accrete, and form a set of rocky planets. Running these simulations over and over shows the possible arrangements of terrestrial planets in solar systems like ours. The process takes place relatively quickly, occurring within tens of millions of years after formation. This is 0.1% of the age of the solar system. Gas giant planets form in an analogous way. There are rocky cores to the giant planets that form by accretion, and then because there's much more material at the periphery of a solar system, they accrete hydrogen and helium mantles, and so become large gaseous planets with the same chemical composition as the Sun. Those planets sometimes migrate rapidly inward, sometimes falling into the parent star, sometimes parking in orbits where we might detect them as hot Jupiters. The stable Jupiters and Saturns take longer to form, and they stay further out, tens of astronomical units from their parent stars. Simulations show how this might happen, and confirm that migration and parking of a giant planet is something that we should expect to happen. What might planets around other stars look like? What might other solar systems look like? Before the discovery of these solar systems, we had no idea. But it turns out that nature is quite imaginative. We can imagine solar systems that might look somewhat like ours, or vastly different. In simulations, anything from 1 to half a dozen or more terrestrial planets are formed, and they're not all the same mass as the Earth, Venus, Mars, and Mercury. Equally, giant planets can form in diverse ways and in diverse numbers. It's very hard to predict how many of these planets will be in habitable zones of their stars, but in general, one or more will be. After decades of searching, many false alarms, and some bitter disappointments, exoplanets were finally discovered in 1995, opening up a new field of astrophysics. From a cold start in 1995, over 3,000 exoplanets are now known, mostly discovered by the transit technique, although for the first 15 years, the Doppler method was the workhorse of detecting exoplanets. The detection limit has marched steadily downward from Jupiter mass to Uranus and Neptune mass to Earth mass presently, and a new area of astrophysics is underway. The properties of the first exoplanets were surprising because they were hot Jupiters, on tight orbits of their stars, completely unlike giant planets in our solar system. But gradually, as the data's improved, we found analogs of our own solar system and even planets that are analogous or similar to the Earth.